inverse function to help us model things. There we go. Just as a quick recap, because we didn't get any questions up on the board, please look at the foundation piece here for this proficiency scale. Is there any part of the vocabulary or the foundation skills that you want to ask a quick question about? So this is the Unit 6 Inverse Functions Proficiency Scale. Yep, that one. So not the one that was just passed out, any of this foundation piece that we need to ask a question about? So feeling confident about those things? Yes. There's always this hole puncher up here. If I ever pass out anything that wasn't hole punch, that means I probably had to print it instead of making copies of it, which means I was behind. Okay. I will say this, please be careful on the features of functions, because at least looking at the demonstrated understandings yesterday and scoring those, we were not 100%, especially on in behavior. So pay attention to some of that. A lot of us crushed it, but pay attention to those functions. And don't forget what's going to happen to the features of a function when we go from the original functions features to the inverse functions features. They'll flip, right? Like whatever the domain was for the original becomes the range, and whatever the range was becomes the domain. Whatever the x's are, those become the y's, etc. Right? So keep that in mind and check it. So I will say this, don't just blindly copy it down, but check your inverse function and check your original function, because if they don't match up, then there's something wrong there, right? So make sure that they are lining up with those ideas of those features flipping. Okay? Anything off of this target section that we know, hey, I want to ask a question about this term or this skill before we practice with today? So as always, you already have the solutions to the check your understanding, right? So you can check your understanding. There's a couple of the spicy ones that, like, if you get to that spicy and you can make sense of the spicy, you're going to be golden, right? Especially like invertible, like that spicy one, that ties into a concept that we didn't get a chance to get to this year that we should have been able to get to, and that's my fault on pacing, / I didn't want to make sure we understood things well, but that'll help in the future. I will, to help support you as you study over the weekend, during second block, record me working through the problems, right, and upload that to YouTube. So I'll narrate, I'll explain those things. This weekend, I shouldn't have anything to grade, and so my entire weekend is going to be dedicated to finishing up planning the last week, making sure that I have a final ready to go, but more importantly, updating proficiency scales for everything. Okay? So please be aware of that I am going to have those proficiency scales upgraded. What I will do, so you can see a quick snapshot, is I will put a score from 0 to 4, which no one's at a 0 on any proficiency scale in this class, so that's good, but a score of 0 to 4 in Power School, so you can see a quick snapshot. But don't forget, if you go to your school email address, I shared the proficiency scales with you back in like August or September. I think it was in August. So you can go in and you can see those proficiency scales. You will need to look at it through like Google Drive or a Google Doc, something like that. But if you just try to pull it up on your phone, it won't look correct. But if you pull it up on your phone through Google Docs, it'll look correct. But you can see exactly what I've seen proficiency with. Once again, I'm going to do the Unit 5 proficiency scales. I'll do the inverse functions proficiency scales this weekend. And I'm going to go back and I'm going to reflect on anything that I didn't see originally and ask myself, can I see this already now? Because it doesn't matter when you learn it. It matters that you learn it. And we want to learn it well so that we are set and prepared for the future. Okay? So, everyone, you can still earn the grades you want. If you're struggling to pass, you can still pass, which I don't think anyone in here is struggling to pass. But if you have a C and you want an A, you can earn it. If you want a B and you want an A, you can earn it. If you got an A and you want 100, you can earn it. Okay, so keep those things in mind. Leah, you came back and got your demonstrated understanding yesterday. That's right. Okay, so We already did this one yesterday. So this is task 3 from lessons 3 and 4. So really quickly, help remind me, what were the 2 models that we developed for the boat, the speed of the boat and the RPMs? What was the predicted speed equal to? Just give me one model or give me the one that we used as a whole class. Should have this in lesson 4. Also should have worked this practice problem last night. So this is task 3 from lesson 4. What is the predicted speed equal to? Should be a cubic function.
0.13h.
Okay, so 0.13x or 0.14 would be perfectly fine, plus something.
1.14.
1.14, so notice if you have a smaller slope, you have a slightly larger y-intercept. If you have a larger slope, like Bella does, you would have a slightly smaller y-intercept. Something around this, but then remember it was cubed, right? Remember we had to take the cube root of the speed to make it linear, so we ended up getting this as our cube, which by the way, that should be RPMs here. And what was our inverse? What was the predicted RPMs then equal to? With that cute little hat, right, Chrislyn? You don't remember you scoffing at me about calling you a cute little hat? Okay.
I remember, that's not cute though.
One day I'll try to convince
Never
you.
even.
Alright, so what's the predicted RPMs? I think it comes out to be the cube root of the speed minus 1.14 all divided by 0.13 or something like that. Does that sound right? Thank you. Got one person. Anybody else? Okay, let me ask a more important question. What are your questions about these 2 models? Either how I got them, before I continue.
Yeah, how did you get them?
Okay, so one, just remember, like I stole this off of the lesson 4 thing, right? But 2, if I want to know the predicted speed, what do I need to do to this equation to get the predicted speed? Cube it, right? So I cube the left side, cube the right side. So got the right hand side cubed. If I want to get the RPMs and predict the RPMs, what do I need to do to the original equation? I still need to use inverses, right? But I need to isolate the RPMs, so what's the first inverse I need to use? Minus 1.14. Right, so we already have the cube root of speed, minus 1.14, and then I would divide by 0.13. Okay, so I just still use inverses. And I will point this out, you can do that from this equation as well, but by using this top one, I took out one step. What are your questions? Okay. So, what I asked you to do last night, hopefully we attempted this, is looking at this first question. If a boat's RPMs in hundreds is 35, and the reason why it says that, because someone was asking me that yesterday. First off, when you look at RPMs in your car, RPMs are usually in what level of number? It's usually in the thousands. And so instead of making my life hard and making this 3,500, this is 3,500. Like I just made it 35, where you have dealt with smaller numbers instead of dealing with really large numbers. Okay, so the RPMs are really 3,500. We're just using it as 35 because we're rewriting all the numbers like that. Okay, so how fast in knots does your model predict the boat will be traveling? Which of those 2 models should I use if I want to know how fast the boat is traveling? Should I use the original, the model for the original set of data, or the inverse?
Inverse.
Okay, raise your hand if you think it's the inverse. I heard way more than just Sarah say we thought it was inverse. Some of y'all are some dirty liars. Who thinks it's supposed to be the original? Okay, so someone give me some reasoning, right? Like you're giving me a claim. Remember, in my class, it's not just about making a claim. What's the reason that so many of us are thinking that we want to use the original? I'm trying to find speed, and this equation tells me what speed is equal to. Literally, you see I'm predicting speed. And also, and more importantly, I want to point this out, what is my input for this equation, for the original? RPMs, right? And what do I have? RPMs, right? I have RPM, so it's easiest to substitute it in and make that the input. What I will point out is this. Hey Sarah, could I substitute 35 into this equation?
Yeah.
Yeah, right? But notice if I do this, I get this. And I want all of us to notice this. This is what I would get if I substituted into the inverse. Versus if I substituted into the original. Which of those is going to be easier to find the speed with? Notice I can just substitute that entire thing into the calculator and just simplify it. Like I could literally type that in as it is. Okay? Sure. Pick up that calculator. Type it in. What is the predicted speed? It was what?
184.
Oh my gosh.
122.
Say it again. It's one.
84.22.
Does anyone know why I reacted like, holy crap? Yeah, I was like, I've never been on a boat that fast. In fact, if you go on a boat that's going over like 60 or 70, that hurts. 60 to 70 on a boat is not the same as 60 to 70 in a car. You got that wind right in your face, those waves hitting. 30 to 40 is pretty fast on a boat. Yeah, I'm not going 184. Ooh, does anyone know what I'm missing in this problem?
This is a predicted. Oh,
Context. Right? Isn't speed measured in knots, nautical miles per hour? Which I still don't fully understand the difference between nautical miles per hour versus just miles per hour. Something about like, I don't know. It's something about the waves and like pretending if the waves are flat or something. I just never fully mastered it. I could go figure it out, but it's just not a priority for me. Questions, comments, concerns, at least about the idea of which model to use.
no.
Jane looks like he's rocking it. No as in no you're not okay, or no as in you got no questions?
No, I know.
The second one, okay, good. I'm glad to hear that. Okay. Alright. So the second question is asking how many RPMs does your model predict the boat's motor will be turning if the boat is moving at 100 knots? Which once again, I don't know what I was thinking when I made these numbers, because that's ridiculous. Please don't ever drive 100 knots. This is one of the issues, it's not driving, what do we call that? Boating? Moving in a boat at 100 knots? I'll have to retool this for the future, because that's just super unrealistic. But in this one, which of those models should I use? Raise your hand if you think I should use the original model to figure out this answer. Nobody. Okay. So who thinks I should use the inverse model? Model for the inverse. Who just has no clue? Who's too scared to answer? At least you're willing to answer that. I got like 5 or 6 of y'all that like haven't raised your hand yet. It's early in the morning, I get it. We gotta wake up. How about this, Sarah? What do you think? Should I use the original or the inverse in this case?
The inverse,
Why the inverse this time?
because we're finding the RPMs.
So we're trying to find the RPMs, and what's my output in the inverse? RPM, sweet. And also, what is my input from the problem? The speed, right? So I'm going to substitute my input in for speed. And so my predicted RPMs is equal to the cube root of 100 minus 1.14 divided by 0.13.
Why don't you just do 100 instead of 184?
Oh, remember this problem was asking about 100 knots. And so actually I want to pause. So before you write this down, I want y'all to think about this. Hey, hold on, Drake. I need y'all to think about this. If I were to let my speed be 184.22 knots, does anyone know what the RPMs would have been? Like if I were to substitute 184.22 in here, anyone know what the predicted RPMs would be? It'd be 35. Why? Well, not just that, because it's the... Say it again. It's the inverse. And what happens when we have an inverse? The inputs and outputs transpose, right? So if I were to let that be my input, in my inverse function, the output would be the original input, right? Like the inputs and outputs transpose. But yes, good question, Landon. But the question asks about 100 knots, doesn't it? All right. So what is the predicted RPMs if that boat's moving 100 knots? And again, please don't ever go 100 knots in a boat. That's how people die.
26.93.
What was it?
26.93.
26.93? I feel like we're missing something with that.
Wait, zero. None of it.
And really, RPMs in hundreds. So actually, 2,693 RPMs. Right? Because it's in hundreds. And you can leave it in hundreds, but just trying to add that idea of context in there, right? These are not made up numbers, they're not random, they are real world context. By the way, based on the previous problem, does that predicted RPMs make sense? Why? Why does it make sense?
Because it's just below where it would be if they were going.
It's definitively below, not just a little bit below, right? Like we went from 184 knots to 100 knots, so should our RPMs drop a good bit? Did they drop a good bit? Okay. Maybe not as much as you might think, because we almost did half of the speed, but remember this is a cubic function, not a linear. That's why it wasn't half of the RPMs. Okay, so we got a cubic function in there. All right. Now I want you all to do one not completely on your own, within your small group. I want us to work on this one here, task 4. Now, with this task 4, I do want to have us all use the same models. So what would be, or what was the inverse model again? I think it was the common log, the body temp was equal to something times the time in hours plus something. What were the slope and the y-intercept that I used?
Negative 0.0.
Negative 0 point what?
87.
87, that sounds right. Plus?
1.99.
Oh, 0.087? That'd make a very big difference, wouldn't it? Plus what?
1.99.
1.99, okay. So let's do this, just so you'll get a little bit more practice with getting these inverses. I know that you would already have it, but I want you to work with this equation. I want you to find the equation for the original model, and I want you to find the inverse. So work with each other, your vertical surfaces. Just again, trying to make sure we're comfortable with finding those different equations. Work with your small groups to find the equation for the original model, what the body temperature would equal, and for the inverse, what the time would equal. So we'll start there, and we'll come back together in a few minutes, because we've done this a few times now. Work with each other, help each other grow and learn, and then we'll do the actual problem afterwards. Okay?
So is that water in there? Yeah.
What were you asking, Sarah?
Is that right there the inverse?
So remember, that equation is very heavily tied to the inverse, but when we have the actual inverse, right, the input has become the output. So what needs to be on its own completely to have the inverse function?
I'm not blind, like, I can see something, like, I can see, it's just small things on the.
What's the input currently in that equation?
You don't have them right now?
No, I haven't looked at it much,
So
actually.
what needs to be completely on its own for the inverse function? Right. So remember, if I want the original model, I need body temp on its own. If I want the inverse, I need time on its own. Rashad, you're fine. Okay. So notationally, I want us to pay attention to this. First off, we realize, hey, the inverse of a logarithm is a what? An exponential, right? We want to hold on to that. The inverse of a logarithm is an exponential. But I need to caution you on this right here. Notice on the right-hand side, they did 10 raised to this variable exponent. That's phenomenal. The only issue that I need us to learn from is this. When we write a logarithm, we're going to see this more clearly today. A logarithm, bless you, is written this way, where whatever's right here is known as my base, which is the same as the base of the exponential. So that's the base of the logarithm. On the left-hand side here, they have not actually used an inverse yet. Same thing over there. Where does the base go in an exponential that most of us wrote it correctly for? It goes in front. Do not forget that the base for an exponential goes in front. When you write the base here, that's the base of the logarithm, not the base of an exponential. Does that make sense? We go with that? Xander, y'all go with that as well? Okay. So now those will cancel. And notice, and this is actually important in terms of notation, notice how I wrote the base in front here? Because also I wrote the base in front here. And so remember, when we write an exponential, the base of that exponential goes in front. Otherwise, beautiful. Down here, only one small thing, and this is being super nitpicky, that I would change here. Does anyone know what I want you to add into this equation? Little hat, right? We gotta make sure it's not just the time, because it's not exact. The predicted time is equal to those things. Remember, whatever my output now is, that's what I'm predicting. So we use those inverses to solve for the variable we want. Again, body temp was the output, time was my input, so now down here, what's my input? Body temp, and what's my output? Time. Remember, those inputs and outputs transpose. What was an input becomes an output. That's it. What are your questions about the solving to get the original model and the inverse at this point? Was this productive to help us understand this a little bit more? Leah saying yes. Thank you, Elizabeth. I got two people. Drake's on it. I don't want to really shake my head because I'm too asleep. Okay, let's do this then. So looking at the problem on the page, it says, use your model to solve this problem. Since the body Detective Paul Costa is investigating was 5 degrees Fahrenheit, use your model to help Detective Costa, which I think I actually rewrote this with Detective LeBlanc, or Benoit Blanc. That's my bad. But help Detective Blanc determine how long the body had been in the freezer. So I'm not telling you what to think about. I want you to use your models to figure out how long had that body been in the freezer. So work with each other. We know that the body temp was 5 degrees Fahrenheit. How long was that body in the freezer? Think about how we're going to figure those. Because when I look at this, and I think through this detail, the whole context was we're trying to figure out how long this person had been dead, right? So do I really ever need the predicted body temperature? No, I have the body temperature. I'm trying to figure out the predicted time, okay? And so these are things to pay attention to. If you ever start watching crime shows, which every now and then that's like my guilty pleasure, like I'm watching, it's not quite a crime show, it's called Tractor. There's also a new one called High Potential. There's always something about, right? So there's always something about dead bodies and how long that person's been dead, and they always use temperature to figure that out. In fact, there was one already this season where they changed the temperature of the house to make it look like the body hadn't been dead as long. Chris is like, yeah, I remember that. Yep.
I love that show.
It's a good time. All right. All that being said, I just want to point this out to you. The beauty of using that predicted time is that I can just type that entire expression into the calculator. In fact, I would do that. I would put parentheses around, and don't forget, one of the things I love about these calculators is the inverses are paired together, right? So when I look at 10 to the x, what's right above it? Log, right? The exponential, the inverse is a log, so control 10 to the x. What's the calculator gonna assume the base is if I don't put anything? So can I put 10 there? Sure. Do I have to? Nope. Minus 1.99, all divided by negative 0.087. 14.84 hours, 83 hours, that's how long that person has probably been dead. That's it. Questions, comments, concerns? This makes some sense. Okay? I want us to already be done with all of the inverse stuff, but I want us to have about 15 minutes to review. So please get check your understandings out. And I want to, let's see. Yeah. So what I want you to do is I want you to look at the check your understandings. You have 4 sets of them. And I just want you to figure out what you want to work on. If you want to work on, does anyone have their check your understandings already out so I can look at them real quick? No, those are proficiency scales. I need check your understandings. If you want to work on determining if functions are invertible, I want you in the ACEs, so that's page 4 and 5. If you want to work on determining if 2 functions are inverses, pages 2 and 3, I want you in this region for the queens and jacks. If you want to work on graphing inverse functions, I want you over here in this region, and we'll use these vertical surfaces. And finally, if you want to work on, and I will say this is actually where the majority of us, quite a few of us should be, pages 8 and 9, finding inverses algebraically, then, because notice that's where we got all the features, where you're actually solving for the inverse function. Let's use the chalkboard for all of that. Yes, please. Like in the original or the solutions one? Okay, I'll probably out for you. Alright, so determining if they're invertible, or if a function's invertible, back here, if 2 functions either given graphically or algebraically are inverses up here. Graphing inverse functions over here at the front, and finding inverses algebraically over here at the chalkboard. Let's get up, let's move to where we want to go. And Bill, I stole yours. Remember, you got your solutions there. And yeah, I'll print a copy out for you.
Mr. Kenny,
Yeah.
can we turn this off?
And what?
Turn this off?
Yes, please. Logging in, but I just want to point out a couple of things. So first things, for those of us who did not do the graphing, I want y'all to hear me clearly on this. And please maybe look at the graphing. So y equals x cubed minus 2. Have we done a lot with cubic functions? Sorry. Yes, not this type of cubic that's just y equals x cubed. That's known as the parent function. I should have said that earlier. Hopefully you talked about parent functions in Algebra 1. If not, it's called a parent function. Don't sweat it a ton. Because here's the thing. How in the world did Sarah get this right here? And why did she get this?
She plugged in the text.
Well, she just chose inputs. And if you have inputs, you substitute them in, and what do you get out? Outputs, right? So she made a table. And because why would this table be helpful when trying to graph?
So you know your point.
Yeah.
So I have my points, and then what about for the inverse? I just transpose them, right? So notice, if I were to maybe get my inverse equation, which I guess that would have been a good thing to do on this one. If I were to get my inverse equation, cube root, not square root. I get x equals the cube root of y plus 2. Now, again, for calculator's sake, we're going to make our input the x. But you know what I'm going to get in the calculator or anything if I graph that function? these input, or this set of points right here, the inputs and outputs transposed. So if I'm trying to graph an inverse function, I'm just gonna get the table for the original function. Substitute your inputs in and get your outputs out. And then, notice, we just had a small mistake and it was stressing Sarah out, but just be careful because the graph looked really funky. And it's just because she had a positive 10 instead of a negative 10. So go back and be careful. Now, does that look like a cubic function we've seen in the past? And then she was like, but this really vertical became horizontal, but if it's a reflection across y equals x, what is vertical is going to become what? Horizontal. The inputs and outputs transpose. One thing over here, what I would point out is, so this is the medium one. Yes, ma'am?
You know how we restrict parabolas?
Yeah.
Would you restrict the purple one?
Fantastic question. What do y'all think? You can get a piece of candy for that question.
The purple?
This purple right here, do I need to restrict it? It's already what? So if it's already one-to-one, is it already invertible? Yes. Remember, the idea is that if you look at this inverse here, is that inverse a function? Yeah. So I didn't need to restrict the domain. If I had this function, when I reflect it, is that inverse going to be a function? Because it would look something like this. Is that a function? No. So remember, if it's already invertible, if it's one-to-one, we don't have to restrict it. Now, Davian, you're the one that was not having fun with this word. There you are. Right? You were like, this is freaking me out. I don't know what to do with that 2. You knew that it was a 3 here, right? Can you just make a table? And start at a 3? Uh-huh. 3 minus 3 is 0. 0 squared is 0. 0 times 2 is 0. What's 4 minus 3? 1 squared? 1 times 2? And by the way, remember, we're going to have to restrict it, so I don't even actually have to worry about these. 5 minus 3? 2. 2 squared? 4 times 2? Can you graph those points? And then so we have these points here. So 4, 2, and 5, 3, 4, 5, 6, 7, 8. And now, what would I do to get the inverse function? All those points I would just transpose. Inputs in to get outputs out. When it's a more complicated function, like the higher degree polynomials, and we're multiplying all those factors, we don't want to do that because there's lots and lots and lots of things going on. But when it's a simple equation like this, just substitute inputs in and get outputs out. Questions, comments, concerns? Go, Demia.
The inverse of the purple function, isn't it not a one-to-one function now?
The inverse of this purple?
No, the pink on the other side.
Well, okay, so you're thinking it's not one-to-one? I will say this, if the purple's one-to-one, the pink has to be one-to-one. And it's probably because you're seeing it super horizontal here, and that's what you're thinking about it. But, and that's more just because of how I graphed it. It technically is still one-to-one, because it is still slightly going up as it goes to the right. Just like, this is super vertical, right? And what was vertical becomes horizontal. So, that's hitting 1 point, that's hitting 1 point. And so it's just that it's getting super vertical, so it looks like it's not one-to-one, but it is still going out as it goes down and as it goes up. Does that make sense? So it is still one-to-one. Good question. You can get a piece of candy too if you want. All right. Or gift it to a friend, either one, I don't care. So let's move into focusing on logarithms. We got about 22 minutes. And so I want to cover some foundational pieces here. So with logarithmic functions, we are going to actually need to tear some pages out of a textbook. So if you look back there, there are a stack of volume 2 textbooks, not volume 1. We actually managed to barely get into volume 2. Actually, we did statistics from it first. But grab one person per group, grab textbook for your group. I need you to tear these pages out quickly and efficiently.
I had my reason.
Did that help? We'll tear out some more on Monday. Hey, by the way, I mentioned this before, but the test on Monday will not be the whole block. It is a very short unit, so it will be a short test.
What What page is it?
So please notice M3 means module 3. That's the first module in volume 2.
Oh, don't touch it, don't touch it.
You can just leave it on while it's not going to take us long to tear these handful of pages out. Yeah, don't worry about tearing out lesson 1. Just tear out some pages from lessons 2 and 3. That's it, lessons 2 and 3. That's the priority.
I don't think that's easy. He said
M3 dash 107 to M3 dash 110, M3 dash 115. Maybe. Might have an answer.
No, thank you. If I would have had a.
Just get good, bro.
All over there.
So, it's an easy does. No, it just ain't that hard. Start from the top. We'll play that. I always start from the top to get a little bit of pace on it. Oh, dang, I just tear it up. My bad. Alright, once you're done tearing it out, just set it under the desk. I'll take care of it later. I'll probably get on that and you can take care of it. You gotta go.
This not, you got some scissors?
They're in the boxes.
Oh, never mind. It's already
Okay. Okay, I have written the lesson 3 pages on the board. You should be done with lesson 2 by now, because I want us to get started. So you'll notice I said lesson 1-ish, because I'm just going to do one quick thing. It's all about linear versus exponential. Lesson 2 is a detail of exponential functions that we haven't covered before, but this will help you with exponentials if you have struggled with exponentials in the past. And then lesson 3 is logarithms. So we'll probably get to logarithms on Monday. Alright, so here's what I want you to do based on the stuff in lesson 1. You don't have pages for lesson 1, so don't sweat it. You have 3 minutes to go to your vertical surface and as a group, write everything you remember about linear versus exponential functions. Okay? So between from the whole class, we should get everything. So go with your group, write everything you can about linear and exponential functions. Think about the graphs, the equations, the table, the rate of change, etc.
Where is Howard?
Lesson 3 pages are in red up there on the board. Say again? Yes, y'all are supposed to be at the front. Talk about it, Kennedy. It's going to help you. There you go. Alright, so a couple of quick things. First off, phenomenal job on remembering the rate of change. Now, the one thing that I'm going to talk about, and I might see some more things a little bit later, is a lot of us remembered a linear has a constant additive rate of change, because we keep talking about that. But what do we need to update about this statement right here? Constant multiplicative. Okay? Constant multiplicative rate of change. Now, there's another problem that is a phenomenal mistake that lots and lots and lots of students make, but I need us to pay attention to it. It's right here. What's the problem I have with this? It says slope, and actually, We're gonna talk more about this in a second, but it should say what? What's that rate of change for an exponential called? It is constant multiplicative, but there was a name for that constant multiplicative rate of change. It was called a constant something. Remember, what do we mean by factors? Things that are being multiplied. That's why we have a factored form of quadratics. Man, that air kicked on hard. So, constant factor. Remember, quite literally, slope means the what type of rate of change? So when I look at a graph like this, I need y'all to pay attention to this. Often I'll talk about what two things define this slope. So change in y divided by change in x, or rise divided by run. So when I do slope, am I adding or multiplying or what? I'm adding.
Pardon the interruption. It is time for our 11th grade attendance incentive. If you'll look at the Excel spreadsheet that was sent and send any 11th graders who are on the list to the cafeteria for a snack. Thanks so much.
I will say this, you can go, but this is really important information. It's your choice. I will not stop a single person from going, 100%. I just also, it kills me that doing this during the middle of class. But go for it if you need to. But slope, notice it's going up and to the right, so what are we doing? We're adding. So when we talk about slope, we're talking about that additive rate of change. Keep in mind that when we talk about slope, we're talking about that additive rate of change. So don't use slope with an exponential function. We need a factor. And so we get this exponential curve in here, things like that. That's great. I'm going to come back to that equation or address it somewhere else a little bit because that's correct, but there's some other things. Ooh, I love this. Remember, algebraically, they have a variable in the exponent, whereas notice this group noted the exponent is a 1. Remember, a linear is that first degree polynomial. Okay. Really quickly here, I do want us to notice, right here, what do we need to update about this statement? This one right here. There's something here. Remember, yeah, I was saying if it's rising, that's a y direction, isn't it? Change in y. If it's running, it's a change in x. And don't forget, m is equal to that, right? So when we say m, and make sure you know this equation, m is my slope, b, 0 comma b is my what? Y-intercept, okay? And so update your equations here. So I know there was a 2 to the x minus 3. That is exponential, but that's not the standard exponential we've looked at. That's actually transformed. That's actually translated down 3 units. Traditionally, what we've looked at is a times b to the x, and that's what I made I circled that one over there. A times b to the x, where a, 0 comma a is my what? Look how I wrote it. It's the y-intercept. Because what have we learned and talked about very heavily this whole year with y-intercepts? The input is? Yes, well, input's always x, but what's the input for a y-intercept? 0. The input is 0. Does anyone remember what b to the 0 is?
1.
It's 1. That's why the a is my y-intercept. B was my constant factor, okay? Now, overall, that seems to be a pretty strong effort. Seems like we remember a lot of stuff. Here's one thing I want to introduce really quickly. We didn't talk about this before, but you remember how this exponential function approached the x-axis? Okay, cool. I got a couple people in there. You'll have that blue chalk that you're using? Thank you. The function 2 to the x minus 3 that's over there would look closer to this. Remember how I said it was translated down 3? And so it would look more similar to this. So this line, you see that dashed line that the function is approaching right there? this x-axis that the function is approaching right there, that's called an asymptote. And it sounds really fancy, but it's not bad. All an asymptote is, and asymptotes show up in all sorts of functions, just not polynomials. An asymptote is a line or curve a function approaches. And I'm going to add one more detail on here that will matter for future things. It doesn't matter a ton right now, but it approaches at some infinity. Notice it approaches this line as x goes to what? What is x going towards? Right, so as x approaches negative infinity, y here is approaching negative 3. So an asymptote is a line or a curve that a function approaches at some infinity. Okay? An asymptote is a line or a curve that a function approaches at some infinity. I know that 2 line erasers. Bunch of thieves over here. I believe it. He's the shiftiest of the lot. What'd you say? You're the one who made it about that. Gosh dang, dude. Messed up. Okay. So please have that note about the asymptote. Again, that definition, that term, so once again, it's a line or a curve, so I put a slash there, a line or a curve that a function approaches at some infinity. Say again. No, you're doing great, because you got to take some notes too. Yeah, you did phenomenal. I appreciate you. All right. So I'm looking now at page 107 in the book, and ideally I always like to do this activity where y'all explored on your own, but for the sake of time, I'm going to present it on the board really quickly, and I'm going to have y'all re-examine this on Monday to really help finalize it, but I want y'all to notice something. Okay, so here it is on the calculator. Right here. So right there, that's an exponential function. We all see that? Hey Miles, can you hit the lights for me? Thank you, sir. So that's an exponential function. How do we know it's exponential? Because it's got that exponential curve, right? Look at the equation I wrote. Where's that variable? And the exponent. Anyone know what my multiplicative rate of change, my constant factor is right now? I would say 1.5, right? Isn't that what b is right here? Okay, so b is 1.5. It's constantly multiplying by 1.5, which is right here. Why, right here, you can see a 1.5. Now, here's what I need you to pay attention to and engage in a whole class conversation about. I want you to make a prediction about when an exponential is growing versus when it is decaying, and then also what base wouldn't even be an exponential. So, I'm going to go through a few different values for b. Okay, so I'm making b nice and large, so I got it all the way up to 3. Now I'm going to go back down. Tell me when you think it changes.
Right there.
Right there. So that's a change. Do you think this is an exponential growth or decay?
Decay.
Why is it a decay?
Because it's starting from going up to down.
Okay, let's use some more mathematical language. As it goes to the right, it goes down. How can we say that? It is
Decreasing?
decreasing, right? Using that mathematical language. Okay, so it is decreasing right now, whereas right here it is
Increasing.
So what values for the constant factor make it exponentially grow?
Positive.
Look at it again.
Older? No.
So if the base is larger than 1, what was it doing?
Increasing.
It was increasing, so it was
Growing?
growing. Notice if the base was 1, is it actually an exponential function?
No.
No, that's linear. And if the base is less than 1, it is decreasing, so it is decaying. But keep watching. Need you to keep watching. Anyone know what our base cannot be in an exponential function? Okay, so the base cannot be negative. So b cannot be, so it cannot be less than 0. Could it equal 0? Was 0 okay? Was 0 okay? Is that exponential?
No.
No, so b cannot be less than or equal to 0. We already said that b cannot equal 1. So when was it a decay? When the base was less than 1, but it also had to be what? Greater than 0. So if the base, and this all is saying, if the base is between 0 and 1, it's going to be a decay. And when is it going to be a growth? When b is greater than 1. That's it. That's exponential growth versus decay. So you can see it graphically, you can also see it algebraically. If you know what your constant factor is, you can figure out if it's a growth or decay. And I apologize if you want to go right now and get your snack, if you have that good attendance, then please go do that. I appreciate y'all staying. Y'all are fantastic. I hope you have a fantastic weekend. Damien, you're my favorite.
He started making a laugh.
And they were staying.
Yeah, I just like let it roll off too. Like, I don't need to do this anymore. You're fantastic. Say again, David. That's all the what?
Pass to come back.
Yes. I'll just email him. Is it Spinks for you?